Everyone, we're here looking at the wave nature of light. We've already talked about it being a particle, but we talked last time about the electromagnetic spectrum and light having different forms.
Yeah, light's basically a form of energy that travels as an electromagnetic wave. All the light waves travel at a certain speed. They change frequency with energy, and wavelength goes along with that.
So now we know that there are these ranges for light from the radio waves all the way up through gamma waves, but a way to prove that light is a wave is through its interaction with each other, what we call its interference with itself. So a good way to show interference is through this simulation. This simulator has a pulse generator here that can send a pulse down to one end, and since that end is fixed, just like a slinky, will hit that end and reflect. How does it reflect?
Well, basically the energy hits the wall or whatever it's running into, and it doesn't have anywhere to go, so it has to go somewhere, bounces back.
And it also bounces back in the opposite phase. So if a crest heads down towards that clamp, when it hits that clamp, a trough is reflected.
Yeah, in this particular instance, that's exactly what happens.
So what we're going to do is I'm going to send a second wave as soon as this first wave hits the fixed end. So here comes wave number 2, and I'll pause them right before the two waves interact. Predictions.
Well, two things could happen. They could sort of run into each other and
Bounce off.
yeah, or they could cross each other and cause problems with the other one.
Okay, so this we'll call this wave A here, and we'll call this one wave B. You can see the height of wave A is about the same as wave B, except wave A is a crest and wave B is a trough. I'll go step by step so we can see what's happening here. And when wave A and B finally do meet, now the two of those are together.
They're gone, it
They're
seems.
completely gone. But that really is the summation of those two heights. The one that was above the line, the one below the line, looks like they've canceled each other out.
Which means if this were a sound wave or a light wave, it would disappear?
If it was sound, we'd hear nothing. And if it was light, we'd see darkness. Now, the question is, what happens after this interference has happened? Well, I'll just hit play, and you can see on top, the crest continues to the right, and that trough continues to the left. So they only interfere when they overlap, but once the overlap is finally over, they just keep on moving like they always did.
Right, because energy is neither created nor destroyed, so it continues.
So to do a different type of wave here, I can switch that end to a loose end instead of a fixed end, and this time when we send a pulse down, let's look at the initial wave versus the reflected wave.
They're happening on the same side of the dotted line this time.
So sending a crest down gives you a crest back. It hits that generator, that's another fixed end, so it does reflect the wave back down, but now the trough reflects as a trough on the loose end. So we'll do the same thing we did again, send a crest, and then send another crest. When these two crests start to meet, when they come back together, what are we going to see?
Well, we should see some kind of interference again.
So by interference, two waves overlapping with each other, and when these two crests overlap with each other, their total heights, their total amplitudes, kind of build into one mega wave.
So in this case, we're adding the energy together, whereas in the other case, we were subtracting.
So we're building here, we're having constructive interference, where last time we had destructive interference. And once again, once the waves pass through each other, they keep on moving like nothing's ever happened. And now you can see with two troughs meaning also build up into a larger trough. How would this work for light? What are we going to see with light?
Well, it'd be a lot brighter.
So we have a bright spot instead of a dark spot.
Right.
And if it was sound, it would be a much louder sound than a softer sound.
Right, so kind of the opposite of noise cancellation.
So light can cancel itself out and build itself up, and due to this interference, any light wave can do this, whether it's visible light, infrared light, ultraviolet, anything in the electromagnetic spectrum, since it travels as light waves, can have this interference pattern. So there's really like two things going on with light.
Yeah, you have particles bouncing off in one case. When we look at our reflections in a mirror, those particles bounce off and we get to see the reflective properties of light in that respect. In another respect, you have waves, which can also bounce off, but they're traveling as electromagnetic radiation.
Part, you could say light has to travel as particles, straight lines. They carry these packets of energy, they carry the photons, and bounce just like tennis balls off the ground, like we showed.
But on the other hand, you have a electromagnetic wave that is reflecting in troughs and crests of waves. And the interesting thing is you have to have both parts of this for light to do the things that it does. You have to have both natures.
So no one's really nailed down, is light just a particle or is it a wave? They've actually just combined it into the dual nature of light. It's both.
It is.
So now that we know how light travels, we know the speed, we know the way it interacts. The only way we know what is out there in the universe. We observe the light we get from distant objects. We see how it interacts with itself, how it interferes, and reveals the cause. So now we need to build some tools to find this light. And we'll do that next time.